Right. Let's go through the whole process now. That what we need to do in order to do a typical machine learning process from begin to end, and we're going to do classification here on those images, is first of all, we have to prepare the data. I'm going to largely skip that out because all data science projects end up having to deal with the mess of the real world. So your data's been badly entered, it's been labeled badly, and you may have to do some massaging of the data to get the labeling right, or to throw out bad values and things that don't belong, and deciding whether the data was fundamentally biased and whether there's some subset of or resampling of that will deal with how badly it was collected, and all of these sort of background things. One key part, though, is you should be splitting it into a training set and a test set. So, just like the way we deal with exams in school, we want to see if somebody's understood their subject by giving them an exam. There is no point giving them an exam on the exact question answers they've just revised. You have to give them questions that are slightly different, or not, because you don't want to test whether they've just memorized a particular value. You want to figure out whether they can generalize what they've learned to something that they haven't seen. So when we get to testing whether this our work has worked, we want to make sure we've not shown the classifier the exam before we run it. So we hold back some of the data. Typically 10% would be, or 5% would be a good amount to hold back. We're then going to create the classifier, which is going through the process of converting the source material to vectors, training a classifier, and then storing the trained classifier. And then we're going to test that trained classifier on our held back test data and measure how well it works. And if it works, it's good. If it doesn't, it's not. This isn't really about checking your work. In this world, we have to we can't be sure what or why it's making its decisions. So we really have to base our confidence in it on testing whether it appears to do the right thing in useful situations. So I'm going to take that data and do the prep step. So I've paired up the character images with the labels that we searched on at the time, because we're going to do this supervised learning here. We're going to give it the answers to the question. The question is, what is this? The answer is Rocket Raccoon. And then we're going to do our split. We're going to split this into the first 60 elements are going to go into the training set, and the last, I guess, 20 elements are going to go into the test set. And now we're going to train based on our training set. As I said, for when things are simple, and by simple, I sort of mean things with a one-dimensional output, and particularly where we have a feature extractor that is already built into the system. So that's things like images, text, time series, sounds, colors, graphs, video, these sort of standard data types. We have feature extractors already built. All we have to do is say classify. And you'll see here that it's automatically figured out that the inputs were images, that there were 4 different classes of output, and there's some hidden things going on here where it's decided the algorithm it's going to use. It's chosen that automatically. So classify has access to about 8 standard machine learning approaches. It's decided here that logistic regression is the most appropriate, and it's trained on 60 examples. And then we've stored that with a name so that I can refer to it later. Now we're going to take our test value that it hasn't seen. Well, hopefully this one it hasn't seen, and say apply that classifier to the thing, and it's got the answer right. And in order to give it the probabilities argument here, to say what does it think this one is? Well, it thinks that near 100% is Star-Lord, and effectively no chance that it's any of the others. Now, it's important to make a distinction here that probabilities here is really a measure of the classifier's confidence, not a measure of the probability that the answer is correct. If we want to know the latter, we need to do further calibration on some of the unseen data to convert these numbers into probabilities of correctness, because it could be that the the classifier simply hasn't seen enough examples to understand that there's ambiguity between different things, or it's possible that it's actually seen this example before, which would make it very confident as well. Hopefully not. I could test, but it doesn't matter too much. Now we can take our kind of test set and I've asked for the first 5 examples from the test set and see how those go. So we know that these weren't in the original, unless there was possibility of duplicate images, which I didn't dedupe for, which is part of the cleanup one might want to consider. But here it's got this one wrong. We can see that is not Star-Lord. That one has got right. This one has got wrong. That one has got right. And that one has got wrong. So it's done pretty poorly this time. There is a little bit of non-determinism in the training, and obviously very much non-determinism in the images I've got. When I play with this example, normally it gets about 4 out of 5 right. And then if I try example 6 through to 10 or 15, it might do better. Let's give it another chance. Correct. Can't tell. Yeah, not sure what that's meant to be. Correct. I think. Correct. Wrong. Correct. So it's done a better job on those examples. But we don't want to be anecdotal about this. We want to be systematic. And so the Wolfram language provides a whole collection of tools to allow us to take that classifier we built, the test set that we held back that it hasn't seen, and go systematically through every element of that test set, calculate what the model says it is, compare it to what we know it is, because the test set had truth values attached, assuming those were correct. And we get back a set of important metrics here. We can access these individually, but actually the key ones all appear on this main panel when we get it back. So the headline thing here is 75% accuracy. So that means that 3/4 of the test examples it got right. Now, that's very contextual. There's 2 things you have to think about to weigh up, is that a good answer? One is, if you knew nothing, then how many would it get right? Well, there were 5 classes and they were equally sampled. So if you just said Groot every time, you'll be right about 20% of the time. So we're trying, 20% of the time. So we are trying to beat 20% here. Well, 75% is really obviously much better than 20%. And the other contextual thing that we need to think about is what's the purpose we're going to put this to? If we're trying to suggest tags for an image, that seems pretty useful. If this is a self-drive car, having a 25% failure rate is a disaster. So we have to think about costs and benefits of using a predictor. Now, actually, it's decided its accuracy baseline is 35%. I'd have to think about why that is not 20. That's the comparison it thinks we should be making. And there's actually about 40 different measures if you want to get technical. But the next most important one is this confusion matrix plot. Let me just make this a bit bigger so we can look at it better. Hit caps lock, that doesn't help. So this tells us the pattern of failures. What we've got is the actual classes on the left and the predicted classes along the top. So what we want to see ideally is everything on the diagonal, that whenever it's actually Gamora, it predicts Gamora. And we can see here that for 2 of the classes, we've got lots going on the diagonal. That Star-Lord, when it actually is Star-Lord, it gets it right every single time, although it slightly over predicts Star-Lord, because when it predicts Star-Lord, actually only 6 out of 8 times it was correct. Sometimes there were things that weren't Star-Lord. So this gives a sense of the nature of failures, because sometimes you get very systematic failures, and you find that there's a particular confusion between 2 different things, and that either tells you, again, from a cost-benefit point of view, does that matter? Well, it depends what the failure is. If it's more likely to do something safe by accident than something dangerous, then you may wish to ignore it. But it also can guide our future data collection, that if it's always getting confused between Star-Lord and Gamora, then we need examples of those 2 classes to help it learn the distinction, and we don't need too many examples of classes where it gets things right. We can also sometimes look for things like the things that it was least confident on, or the things that it was most confident on, in case that helps to tell us that, in fact, the data's been polluted. For example, if there's a lot of worst classified examples and we look at them and go, actually, those don't belong in the data set at all, that can send us back to improving our data collection techniques. So I said this classify command has a whole bunch of different methods. So that raises the question of which does it use and when we should use different ones. Here I've got just as a fresh example, some numbers that map to colors. I don't know why, but that maybe this is something like the geolocation on the world, and that's the dominant color of the flag or something like that, and we want to make some kind of prediction. What we get is, by default, is we have method goes to automatic. You don't have to say it when it's automatic, but if I want to say it explicitly, that's the default value when we use classify, which is why it's decided on its own to do something, in this case, naive Bayesian. Now, we can control that if we want to by saying, okay, I don't want that to be automatic or naive Bayesian. I'm going to use, say, gradient boosted trees as a method. And now we've forced it to use a different method, which will have different characteristics. And if we look at, I've made this a little bit big on screen. Let's make that a bit smaller. From a set of original data, we're trying to fill in the spaces with our predictor. You can see that depending on the method you use, you get quite different behaviors of what happens as you cross from one area to another. That nearest neighbors is basically saying, if we're looking here, we look at the things that are nearest, and they're all blue, therefore it's blue. Logistic regression is fitting kind of trend curves to it. So it's trying to find lines that kind of switch in a logistic curve in a true false in a smooth kind of way, lines across the data that switch between zones. Support vector machine, I'm trying to remember the details of. I forget the details. Random forest is building decision trees and in random orders, and then seeing how many of them make good predictions and discarding the poor ones. Naive Bayes treats the two variables as variables somewhat independent. That like spam filters work very much like this. If I get email that says buy cheap Viagra, Viagra is a negative word, cheap is a negative word for spam. If I get email that say Mathematica or webinar, those are positive words, but it treats them independently. So if I had a webinar about Viagra, it would those things would cancel out, is the naive Bayes approach. And neural networks is the kind of the richest approach, which we'll spend the last third of the webinar on. So the way you choose the method, I'm going to skip through this example, I think, otherwise I'm in fear of massively overrunning on time, is basically to try each one, possibly on part of the data if you have very large amounts of data, and then use these measure approaches to decide which one is doing best. And in fact, that's effectively what classify does when you use method goes to automatic, is it starts to train a little bit of the data on each method, measures their performance, and discards the methods that are performing poorly until it ends up with one method left that seems to be the winner, and then it puts all of its training effort into that. For this small training set, it probably trains all of them completely, but for a large training set, it will do that with a reduced sample until it does better. And even all the subparameters, because all of these methods here, like gradient boosted trees, has half a dozen parameters I can say, which is a boosting rate and a gradient measurement function, all of these things I can spell out. Those things, again, trial and error and measurement is the only real way to figure out how to tweak these things to give the best performance. Now, prediction, I'm going to skip through this very quickly as well, because predict, we have a high-level command for predicting numerical values, but it works exactly the same way that classify does. So I've got this data set of about 20 properties of house prices in Boston. This is a classic old training set. And here's the first 10 properties. And I do exactly the same thing. I split the training data into training and test. I do exactly the same thing as before, except this time the syntax is slightly different. I'm saying I want to predict the house price. The medver, I think, was the label for the medium value, was the thing that we're trying to predict. So we're taking our training data, but that's the value out of that data we want to predict. I've given some other property here to tell it to try hard. And now I can give it some unseen values and it predicts that this is a $19,000 flat. As I said, the data's very old, so you'd be lucky to find a $19,000 flat in Boston now. The measurements, again, the principles are the same, although the actual measurements are different for continuous data. So we have to look at things like the standard deviation, that our predictions were plus or minus about $2,500. We want our data to lie on this line if we can, so we can start seeing that the biggest outliers are for the very high prices, it would seem, and there doesn't seem to be a great asymmetry. So we can get sort of qualitative measures from that. But again, there's about 20 measures we can use if we really care about the details.